Welcome to Grandeur Decoded, where we dissect the world's most spectacular achievements and reveal the strategy, engineering, and audacity behind them. Today, we are going inside a mansion that looks like a backdrop for a period drama, but was one of the most advanced pieces of residential engineering on Earth. The Biltmore Estate is known as America's largest private home. What almost no one understands is what it actually took to build, power, and maintain a 270-room stone palace on a remote mountain slope in the 1890s. This is not just rich person excess. It is a prototype for the modern mega house, wired and plumbed at a time when many American cities still did not have reliable electricity or clean water. Here are 10 decoded facts about the Biltmore Estate and the deep engineering that keeps this American giant alive. This is the first fact. The scale of Biltmore is not just impressive. The house covers more than 175,000 square feet under roof and rises up to a central tower that stands over 250 feet above the basement. Architect Richard Morris Hunt did not rely on guesswork to keep that mass of Indiana limestone in place. Beneath the ornate facades is a carefully calculated skeleton of steel beams and masonry arches that distribute weight into a network of piers and load-bearing walls. Hunt and his team used structural calculations that were advanced for their time, adapting methods created for public buildings such as train stations and opera houses. In a period when many large homes were still framed mostly in wood, Biltmore was designed with the mindset of a civic monument. This is the second fact. To even make construction possible, George Vanderbilt had to create an entire logistics system from scratch. The site outside Asheville, North Carolina was rural and underdeveloped. To bring in stone, brick, steel, timber, glass, and machinery in the volumes required, Vanderbilt financed a private railroad spur from the main line directly to the estate grounds. Train cars rolled in carrying everything from limestone blocks to boilers, kitchen ranges, and elevators. Near the site, Vanderbilt funded kilns that could fire tens of thousands of bricks a day, plus a woodworking shop that turned raw timber into interior trim. Between 1889 and 1895, the project consumed thousands of tons of materials and required a coordinated schedule very similar to a modern infrastructure project. This is the third fact. The choice of Indiana limestone was not only aesthetic, it was an engineering decision. The stone used for Biltmore came from the Hallowell Quarry in Indiana, part of a limestone belt known for its uniform grain, predictable strength, and ability to be cut into large blocks without cracking. At a time when transportation still depended on steam locomotives and horse-drawn wagons, shipping heavy stone hundreds of miles was a serious commitment. The team tested different stones for compressive strength and weather resistance before settling on the Indiana material. Once at the site, stonecutters shaped the blocks in a masonry yard, then cranes and hoists lifted them into place. The precision of those cuts and joints is one reason the structure has survived more than a century of freeze-thaw cycles with little structural movement. This is the fourth fact. Under the romantic image of a French-style chateau is a serious mechanical heart. Biltmore had electricity in every major room at a time when many American homes were lit by oil lamps and candles. Vanderbilt installed a dual electrical system, drawing power from the local grid when possible, but also from a private hydroelectric plant built on the estate. Engineers diverted water from a nearby creek through pipes and penstocks to drive turbines that spun generators. Those machines sent current up the hill to the mansion, where insulated wiring fed chandeliers, wall sconces, electric bells, and one of the early Otis elevators in a private residence. Backup boilers and steam systems meant that even if one part of the system failed, the house could continue to operate. This is the fifth fact. The plumbing and sanitation systems at Biltmore were decades beyond what most Americans experienced. Contemporary accounts describe 43 bathrooms with full running hot and cold water. To make that possible, engineers built elevated reservoirs and pressurized tanks that stored purified water collected from estate springs and streams. Mechanical pumps pushed the water through a lattice of cast iron and lead pipes snaking behind walls and under floors. Wastewater flowed into a separate drainage and sewage network designed to carry effluent away from the hilltop and reduce contamination near the house. Vanderbilt spent heavily to make sure his mountain palace did not share the same disease risks as crowded cities. This is the sixth fact. The air inside Biltmore was engineered long before the term climate control became common. The house combines natural stack ventilation with mechanical assistance. High ceilings, tall windows, and interior transoms encourage warm air to rise and escape through vents near the roof, while cooler air is drawn from shaded sides of the building and from the basement. In key areas, especially the kitchens and smoking rooms, Vanderbilt's team added powered fans and metal ducts to pull hot, smoky air out and discharge it above the roofline. Combined with thick stone walls that buffered temperature swings, this system allowed relatively stable indoor comfort even in southern summers without the electric air conditioning that would come decades later. This is the seventh fact. The estate grounds functioned as an early environmental engineering laboratory. George Vanderbilt hired landscape architect Frederick Law Olmsted, who saw beyond gardens and scenic drives. The land around Asheville had been heavily logged and farmed, leaving hillsides eroded and vulnerable. Olmsted persuaded Vanderbilt to invest in scientific forestry, replanting large swaths of the property with carefully selected tree species, terracing slopes, and controlling runoff. Forester Gifford Pinchot and later Carl Schenck used the estate to test sustainable logging practices, measure tree growth, and manage watersheds in a controlled way. This work turned Biltmore into one of the birthplaces of professional forestry in the United States and influenced the later creation of the Pisgah National Forest. This is the eighth fact. Beneath the guest rooms and grand staircases is a network of service corridors and mechanical rooms that operate like the back of house in a large hotel. The basement level contains industrial laundries, wine cellars, cold storage rooms, boilers, electrical switchgear, an elevator machine room, and staff dining areas. Food traveled from storerooms to the main kitchen, then up through dumbwaiters and service stairs that kept servants moving behind the scenes. Engineers planned circulation so staff could move quickly between laundry, kitchen, and guest floors without crossing public spaces unless necessary. That layout was a deliberate attempt to create a logistics system where linens, dishes, coal, and supplies could flow constantly, while the public rooms stayed calm and theatrical. This is the ninth fact. The economics of building and maintaining Biltmore look less like the finances of a family home and more like the accounts of a public works project. Construction costs are usually quoted around $6 million in late 19th century currency. Adjusted for simple inflation, that is well over $200 million today. Adjusted by share of national economic output, the figure moves into the multi-billion range. The payroll for construction workers, artisans, engineers, and domestic staff ran into the hundreds of thousands of dollars a year at a time when the average American worker made less than $500 annually. Biltmore effectively functioned as a company town, employing local residents in construction, farming, forestry, and hospitality. When Vanderbilt's fortune began to decline, the carrying costs of such a complex helped push the family to open the estate to paying visitors. This is the 10th fact. Keeping Biltmore standing in the 21st century requires as much technical care as many infrastructure projects. Conservation teams track humidity levels room by room to protect paintings, tapestries, and wood paneling from warping and mold. Structural engineers survey the stone facades with laser scanners to detect tiny movements or cracks that might signal deeper problems. Specialists study the original mortar recipes and stone tooling so that repairs blend with 19th century work. Mechanical engineers design upgrades to heating and cooling equipment that can fit into existing chases and rooms without gutting historic fabric. Even the surrounding forests and watersheds are managed to control erosion, protect views, and maintain the balance that Olmsted envisioned. The Biltmore Estate looks like a museum piece, but in reality it is a living engineered organism under constant careful supervision. The deeper you look at Biltmore, the less it resembles a simple mansion, and the more it looks like a private city built around one family's vision. It pulled industrial-era logistics onto a remote mountain slope, hid hotel-scale machinery behind carved oak and stone, and helped launch American forestry and conservation science. The project pushed the limits of what residential architecture could be in its time, and its survival still depends on the same kind of multidisciplinary engineering that created it. If you want more deep dives into the hidden systems behind the world's most spectacular achievements, subscribe to Grandeur Decoded and stay with us as we continue decoding how human ambition reshapes the world.